Today, we are going to be solving problem 1. Problem 1 wants us to identify the starting material, diene and dienophile, that would be needed to make the Diels-Alder product shown below. So first, let's draw a 2D top view of the product. When forming Diels-Alder products, we must be familiar with this process. So 1, a new sigma bond is formed. 2, another sigma bond is formed. 3, a pi bond is simply moved. If we are to deconstruct the product to get the starting materials, we'd simply just have to do all these steps in reverse. So let's start with step number 3. A pi bond was moved from its original spot. So this pi bond actually used to be here. So let's place that here. So I'm going to draw the backbone structure and move it over here. In the next step, a sigma bond was formed. So the sigma bond that is formed between the diene and dienophile are here and here. And the sigma bond formed here came from a pi bond over on this structure. So let's draw this out. We're putting this pi bond back, and notice in the middle there's a bridgehead structure. So let's flatten out the bridgehead structure. And this is our diene. How do we know this? Well, there are 2 double bonds present between carbons. And this is our answer for 1A. Now let's get our dienophile. So here's the backbone structure. So we're putting back the pi bond right over here. So that means this will be in a double bond form. And lastly, we need to include the substituents. So the substituents were both facing downwards, meaning it's a cis conformation. The cis conformation must be maintained as the stereochemistry found in the starting materials is the same in the products. So our substituents will also be in a cis conformation. Therefore, this is our answer for 1B. 1C. In the reaction below, the major product is missing several substituents. Note that the stereochemistry of one substituent is fixed and you cannot change it. To solve this problem, let's draw out the diene and dienophile. So we drew out the diene and dienophile, where the diene is this structure, and the dienophile is this structure. So we will still follow the same steps listed in the previous question, where first a new sigma bond is formed, another sigma bond is formed, and we just simply move a pi bond. This pi bond right here will move over here to form a new sigma bond to connect the diene and dienophile. And that checks out step 1. Step 2, this pi bond forms a new sigma bond to connect the diene and dienophile. So that checks out step 2. And the last step, we move a pi bond. So this pi bond will simply move over to this spot here. Okay, that checks out. Next, we need to care about the stereochemistry. So let's check out the stereochemistry of the dienophile. Since both substituents are facing the same direction, which is this way, relative to the double bond, the substituents are in cis conformation. We need to keep this in mind as the stereochemistry in the starting material will be maintained in the product. Now let's check out the stereochemistry of the diene. So these two methyl groups are trans to each other. So the relationship is trans, as they are facing opposite directions. The ether and the methyl group are in cis conformation with one another, as they're facing the same side. So now let's make our product with this information. I'm starting with the diene backbone, just drawing out this structure right here. And for now, we're not going to mind as we are drawing this, we're not going to mind stereochemistry, as we're just trying to get the skeleton of the structure down. So we'll still maintain our substituent here, and our methyl group will get out of the way so that the newly formed sigma bond between the diene and dienophile can exist. So that's this bond right here. Now we're starting with the backbone of the dienophile. So the dienophile starts here and forms a new sigma bond here. And the pi bond that was previously here on the diene will move here. Now let's include all our substituents. So we had a methyl group down here. We also had another methyl group over here because of the dienophile. So this methyl group right here came from the diene. And the last group we add is this right over here. Okay, so now we have all our substituents down. Let's now mind the stereochemistry. So we said the dienophile had its substituents in cis conformation, meaning that they must face the same direction. Since in the problem, we're already given a substituent in the downward direction, we will follow that. So let's erase. Methyl is in cis conformation with this structure, therefore it is also facing downwards. Now let's look at the stereochemistry of the diene. So we set the ether and the methyl group down below. The ether and the methyl group down below were in cis conformation with one another. Therefore, if we're making the ether dash form, the methyl group below should also be dash form, facing away from us. Now, we also said that this methyl group and this methyl group were trans towards each other, meaning they're in opposite directions. So the methyl group at the top should be in dash form. Therefore, this is our structure for 1C, and it checks out. This completes problem 1.